Thank you. This work comes from a collaboration between electronic laboratory and telecommunication laboratory in my university, and is basically about the possibility of realizing a sensor network based on RFID. Everybody knows very well what is radio frequency identification is. These tags are used everywhere for anti-thieving purposes in shops or for ticketing, for electronic ticketing. But they are essentially stupid devices in the sense that they start working when they are in the range of an electromagnetic field. In this case, they start transmitting a code, basically a code contained in their memory. But what if we can? What if we transform these devices, let's say stupid devices, in sensing devices with sensing capabilities? And additionally, what if we try to make a network of these devices? The advantage, the clear advantages of this solution would stay in the fact that these devices are in fact batteryless. They don't need power. They just receive power from the reader, from an electromagnetic field. This talk, in this talk, I will briefly introduce the idea of RFID sensor networks and the possible benefits that will come from this technology, and I will present an enhanced RFID tag designed in order to permit the fabrication of the construction of a network of such devices. I will then show a simple network model in order to evaluate the performances of this approach. You see here a very rather famous RFID tag with some intelligence on board. That is the WISP, developed by Intel a few years ago. The device does not have a battery on board, and it starts working when when it is in the field of an electromagnetic field. In fact, these devices have a lot of advantages. First of all, they have native identification features in the sense that they have on board the same characteristics. They do the same work of a standard RFID tag, consume very low power because, of course, they don't have a battery on board, so must be designed to work with the minimum energy. And after all, they have also a simple design. There's a simple design behind, for instance, in the fact that the same interface, radio frequency interface, is used for communicate and for collecting energy. What have we targeted in this study? We wanted to evaluate the feasibility of a network of such devices deployed in a large area for long run, let's say for perpetual applications. This poses some challenges that need to be studied in somehow. On the front of the hardware, we need to enhance the sensor tags, enhance the design, the electronic design of this device by improving the energy harvesting capability and improving and reducing the power consumption. On the application side, we have to make clear somehow how we plan to replenish of energy these devices and how to collect data from them. let's start from the basic the device, which is the core, let's say, of this technology we are proposing. It's a tag that you see here, which is from left to right. We have the dipole antenna tuned for the ultra-high frequency standard for radio frequency identification tags. The first stage is an impedance matching circuit I will discuss soon after, which is a new part of this, it's a new block in this design. The second block in the middle is the harvesting circuit, which is made of a rectifier, standard rectifier, a storage capacitor, this one, okay, a storage capacitor, which need to be replenished from time to time in order to allow the old device continue working also when it is out of the electromagnetic field. Power management stage, and finally a microcontroller, ultra low power microcontroller unit that organizes the work of all this stuff, which is connected directly to the sensors, any kind of sensor. And this is also a novel approach. We have added a standard RFID tag, which has in itself the capabilities, which warrants the possibility, has the capability of communicating outside using the proper standard. Now, concerning the energy harvesting section, this was made, all the chip is made with off-the-shelf devices. Let's start from this. And in particular, the energy harvesting circuit is summarized here. It's based on Schottky diodes. They are necessary for their low threshold voltage. And it's a standard 5-stage Dixon topology. The output voltage here, of course, changes a lot when according to the power received by the antenna, which is placed here. So you need to regulate this output in order to obtain a flat voltage that is necessary to power the rest of the circuit. And for this, we use a low dropout regulator with very low consumption. The surplus power is stored in this capacitor and will be used for the functioning when the device is outside the reach of an radio frequency field. The impedance matching circuit, which was the section on the left, as an enhancement in the fact that the circuit is continually tuned in order to get the best, the highest energy from the antenna. The problem is here that the circuit, the energy harvesting circuit, is made of nonlinear devices, basically diodes, which means that these devices, being nonlinear, make that all the circuit is nonlinear. So there is not a fixed, a given impedance, and the input impedance here changes with the power entering from the antenna. So by introducing this variable capacitor and this fixed inductor, we can continuously tune this filter and always get the highest energy, the highest possible energy from the antenna. And this is organized by the microcontroller. So let's apply this device to the idea of a network of them. We assume that the Devices like this are distributed randomly in a large area. A large area means a few hundred meters by few hundred meters. They are rather far each other, say 10 meters far distance between them approximately. We can have two approaches. Either one mobile reader that visit all the tags and replenish and recharge the capacitor, or have multiple mobile readers. So the problem is to determine the minimum number of mobile readers to guarantee perpetual network operation. To do this, we have we studied. Where is the model we have constructed? The model is based on these considerations. The time to recharge a single tag is the ratio between the energy stored and the power that is collected by the antenna. The energy stored depends in turn on the it can be calculated according to this formula. Here we have considered that the energy due to the lowest working voltage is useless for the functioning of the circuit. So only the voltage that is above VDD can be used for energizing the system, and the power we can collect can be calculated by the standard Freeze equation in free space, where these are the gain of the two antennas receiving and transmitting. This is losses due to polarization, and this is the rectifier efficiency, wavelength. This distance, and beta is a parameter that adjusts this equation for short distance applications. In order to guarantee perpetual network operation, we have to recharge each node periodically. The lifetime, which means how long a device can work when it is fully charged, can be calculated as the ratio between the energy stored in it and the average power dissipated by it. This is the power in action, and this is power in sleep mode. And there is a duty cycle which is a changing parameter. The maximum time between two visits cannot exceed the lifetime of the sensor and the time that we need to charge it, the time that is necessary to charge it. We then define this network. We find the shortest path, and then calculate the travel time, which is the length of the path divided by the velocity, and the time to recharge each sensor. Time charge times n, which is the number of sensors. When we have multiple readers, here R2, R3, R4, R1, the minimum number of them is given by the ratio between the time that is necessary to recharge all sensors divided by the time that necessary to recharge one sensor. Here comes the results. First of all, I show that our sensor, our device, has a high efficiency in collecting energy compared to a WISP device. We see, for instance, that a distance of 0.5 meters, we can collect roughly 2.5 milliwatts when it is the reader has 1 watt power, while with the WISP we are much lower. This is due to the fact that our tag has a high efficiency, rectifier efficiency compared, is double compared that of WISP. Then we put all together into a model we gave it to MATLAB. We put into a MATLAB model, and then we made several simulations. And here are the parameters of this simulation. We made a number, but we consider, for instance, a number of sensors comprised between 50 and 300. This is the area and the distribution in random. Here are the results. Finally, what we see here is that our sensor, which is characterized by the broken lines here, broken line, requires a number of readers, which is much lower than the WISP sensors. And this is independently of the time. Here is 1 second, 50 seconds, 30 seconds, represents the operation period of this sensor. It collects data every 1 second, every 50 seconds, every 30 seconds, and so on. So there's a clear advantage in this in using this new tag. These are the conclusion. I will skip at them as I'm running out of time. I think I just want to conclude with this, which is what comes next. Is that a microchip that we have designed that includes all of this in a single microchip, a 1.5 by 5 millimeter sized. It has a temperature and a light sensor on board, a 2.5 gigahertz oscillator, and the antennas, which is a dipole antenna and a loop antenna on board. They are all used for transmission, a converter, control logic, and so on. So next time I will show, maybe next year I will show the characteristics. It's only designed, it is in fabrication right now. And thank you for your attention.